So, okay, let me briefly recap on scattering and the general formulation of scattering. Okay, so this I didn't do so well last time. So just let me bring up the sketches, Jordan sketches, and I think it'll become clearer right away. Okay, so as I explained last time, we have this physical problem where we have an incident plane wave and a monochromatic plane wave hitting an obstacle, which is some solid material. For us,
Professor, Nidya is waiting in the is waiting for to enter.
Okay,
sorry.
That's good. Thanks for saying. So the incident radiation interacts with the microscopic charges distributed in the obstacle, which radiate away, and those this radiation that comes away from the obstacle is called a scattered wave. Okay, so we have an incident wave, we have fields inside the obstacle which generate the scattered wave. Okay, so we saw that inside the field, the incident wave can be written as a plane wave. Okay, so there's no news here. Okay, and to fix ideas, we'll first consider just the case of Rayleigh scattering, which is a case where the maximum dimensions of the obstacle is much less than the wavelength. In general, this is a notation we'll follow. Subscript 1 refers to inside the obstacle, and subscripts 2 are outside the obstacle. Okay, so the other thing to remember is this scattering plane definition. We have a z-axis aligned with the incident beam, and we're observing the scattered radiation towards a direction r. So which this defines the plane, right? We have the plane of the radial vector defined by the radial vector along with the z direction. So these two vectors define the scattering plane, and we use a set of a basis vector, a set of vectors for as a basis, which is defined in terms of the scattering plane. So we have a unitary vector perpendicular to the plane, which is E perpendicular, and the other one is E parallel. And they are related to the spherical coordinates, right? We have them in equation 7 here. So E parallel is the same as E theta, and E perpendicular is the opposite of E phi by convention. Okay. We decompose the incident and the scattered waves. So these are the electric fields, of course. We decompose the incident and the scattered electric fields on this basis of on this new vectorial basis. Okay, so here going back, here is E incident perpendicular and E incident parallel. So this is the parallel. This is the perpendicular one. Okay, this other one is evaluated in the direction theta. So at this point R, if we evaluate the fields here, at this point R, then we have this basis vectors, right? So this is were you seeing my screen okay? Are you seeing my screen? Is it okay?
Yes.
Okay, because I had a message just now. All right, so yes, so you of course these are vectors, right? So you must think that this E parallel and E perpendicular. Yes, so these are. Hold on a second. All right, yes. So this is one important detail to remember here. If you notice, the incident wave is decomposed into these perpendicular and parallel vectors because this is a convenient basis to represent the polarization of the incident wave. E parallel and E perpendicular represent the plane that's orthogonal to the incident beam. So of course, these vectors here can be moved around, right? This is just a convenient way to draw it. This is a 3D render, you must remember, and this is actually meant to be orthogonal to the vertical axis, which is the incident beam. I hope that's clear to all. The incident vectorial basis is meant to be orthogonal to the incident beam, okay? Which is good enough because we are using electromagnetic waves and they're transverse waves. And then when we look at the scattered wave is propagating in this direction. We are observing the scattering in direction theta. And so we also need a basis of vectors that's orthogonal to the propagation direction. And this is why we introduce the perpendicular scattered and E parallel scattered, which is different from the basis of vectors we use for the incident radiation. Okay. So these are two different bases. But we can decompose the incident basis into the scattered basis and vice versa. So away from the induced dipoles, we know that in the far zone we'll have radiation, and the radiation in the form of a spherical wave whose radial modulation is like this. So it's an oscillating exponential divided by R. This we saw in the last chapter, okay? And so we saw also last time that there is a linearity between the scattered wave and the incident wave, okay? Because of the linearity of the Maxwell equations. I'll give you an example by imagining that, for instance, first we consider a linearly polarized incident wave, so only with this component and zero perpendicular component. And then as a separate problem, you consider just the opposite situation where you have only the other polarization, okay? And both fields interact with the obstacle, and they re-radiate. And of course, because of the principle of superposition, which is also another way to call the linearity of the Maxwell equations, if we sum up both incident fields, then the outcome is also going to be the sum of both. Okay, this is what inspires this idea of introducing the amplitude scattering matrix. So we know that the radial amplitude is going to be a spherical wave. The problem is to know the angular dependence. The angular dependence is condensed into these four coefficients. Okay. So in general, the time average pointing vector outside the obstacle is defined so, because subscript 2 is region 2 outside the obstacle. Okay. And when you do the calculation, you know, adding in region 2, we have the incident and the scattered field that superpose. So we have two fields, the incident and the scattered fields in region 2. Let me write it down. E2 is E incident plus E scattered. Okay. And this is what we need to plug into, and the same with H. Okay, of course. H2 is also H incident plus H scattered. And so when you do the math and you plug it in, this is what comes out. We have this crosstalk term, which is labeled extinction. And this is the part I'd like to explain a little bit better now. We calculate the Stokes parameters in the same way as we did in the polarization section. And we can relate the Stokes parameters of the scattered wave with the incident Stokes parameters with what's called the scattering matrix. So the scattering matrix is what ultimately controls the transfer of radiation. Okay, so when we want to do the full-blown radiative transfer, we need to consider this scattering matrix. Okay. Good. So about the extinction. Now, this is the idea. We have incident radiation that's interacting with a particle here. Okay. Now, imagine that there's no particle. If there is no particle, the net flux of the incident radiation through this imaginary sphere is going to be zero, right? Because of symmetry, everything that comes in comes out. There's no sink and there's no sources. There's nothing inside the imaginary source, the imaginary sphere. Okay. However, suppose that now we compute this quantity, and I'm not going to put any labels for now. So this is going to be S dot dA across some surface A. Okay. So this is a surface A. Right? So imagine that we have a star at the center here. Okay. Of course, then we know that W is going to be the stellar luminosity. Right? It's going to be the stellar luminosity, the power emitted per unit second, because this is the flux per unit area. Okay, good. Now imagine that we don't know what it is. It's not a star. It's whatever. Okay, so we have the situation we have been considering now, which just to fix the idea, we have a sphere. Okay, and we have something inside, an asteroid. Okay, whatever. Can be a grain or a dust particle, a ball of glass, who knows, okay? And we compute the same integral, okay? Now, what happens if it turns out that W is negative? What would be the interpretation of it? I'm gonna put it the other way around. I'm gonna say what happens at first. Let's see what happens if W is positive. We have the same situation as a star. We have net output luminosity. Now, if W is negative, what happens then? What do you think is going to happen?
It's absorbing it somehow.
Yes, because of course we have absorption. We need to conserve energy, right? If we lose a flux of radiative energy, if we lose radiation flux, it's got to go somewhere. Because there's going to be a sink that absorbs all this energy, okay? So if we say that S is the total Poynting vector in space, S is the flux of radiation anywhere in space, okay? So S depends on position, okay? And this is the net Poynting vector anywhere in space, okay? And I calculate the flux of it through the sphere. If it's positive, it means that luminosity is being emitted away from whatever is inside the sphere. Could be a collection of stars, okay? If it's negative, it's the other way around. It means that radiation is lost somewhere inside it, okay? And if it's lost, it's got to go into something because of conservation of energy, okay? So this is why we call this integral the absorption part. And for convention, we are going to give it a minus sign. So that if it's positive, it means we have an absorption, okay? So we now define WA as minus the integral of S dot dA. And this means that WA negative means absorption. Okay, so now I hope this is clear now. I wasn't very emphatic on this last time. Now I think it's become clear. So WA is this integral of the net Poynting vector and its absorption. Now, if you decompose the Poynting vector as in equation 9, so this is what we just saw, equation 9, saw that the Poynting vector outside the obstacle is the sum of the incident Poynting vector, the scattered Poynting vector, which is that of the scattered wave, and the crosstalk. Okay, so we put it in, we plug it into this flux, okay, and change the definition of signs with this new W's. So W incident is just the minus, but W scattered has got a plus. Okay, and we put a plus because what we want to say here is the net luminosity scattered away from the obstacle. Okay, so when this is positive, it means that it is indeed scattered away. Okay, it's consistent with the idea of scattering. Okay, so that's why this one has got a different sign from the others. Now we plug this in, and we remember that the flux of the incident beam through a closed surface is going to be 0, because there are no sources or sinks in the absence of an obstacle. So this is 0 by symmetry also. So this one is 0, and we have left with WA, and this is what we're left with. WA is minus WS plus W crosstalk, this extinction term. And now we turn it the other way around in equation 24, and we write the extinction part, W extinction, is the sum of whatever is absorbed inside the sphere and whatever is scattered away. But this is exactly what we defined in terms of the radiative transfer in chapter 1. We saw that, well, in order to describe, to parameterize the transport of radiation, we included two absorption coefficients. We had an absorption coefficient and we had a scattering coefficient, okay? So, and the result of summing both of them, then the result was the total extinction, is whatever is removed away from the beam, okay? So this is why the crosstalk term is called the extinction, and it's composed of an absorption term and of the scattering term. Is that clear now? Okay, yeah, good. So what follows afterwards is just very painful and tedious calculations. We want to relate the extinction with the scattering matrix and calculate the phase function. We first considered the case of a linearly polarized wave where the incident field is parallel to the x direction, and you can work out that the scattered fields are given by 26 and 27 if we've given the amplitude scattering matrix. Okay, and yes, so this angle phi is the spherical coordinates phi. Okay, so it comes from decomposing the incident basis onto the scattered basis. We can calculate the flux of the Poynting vector outside a sphere, through a sphere of radius r. Okay, so now remember, we're considering that the sphere has got a so Wx would be the integral of s dot dA through a sphere, and that's a sphere of radius r. Okay. Oh, let me write down the area of the sphere. Okay. So this is the flux of this of the total. Oh, it's got a minus sign, I think, also. Okay, let's put the minus sign. So we have S because we have the total Poynting vector because we have the incident electric field and we know the scattered field. And outside the sphere, the total field is given by the sum of both, right? So E is simply EI plus E scattered, etc. So I give you this as a homework. But I think it might still be good for you to do it. But I mean, it's not the end of the world if you don't. Try to do it, because I think this way you'll be able to better understand what we're trying to get to here. But once you work out the mass, then we introduce this extinction cross section, which is the ratio of the the flux that's removed from the incident beam relative to the incident beam. So following this decomposition, we decompose this extinction cross section into an absorption and scattering part. Okay. And using equation 25, which is right, so the scattered component, and equation 26. So right, so this is the electric and the magnetic fields. Equation 25 was the electric and magnetic fields. Allow you to calculate the cross section corresponding to WS. Okay. So WS is just the scattered part. Okay, it's the same integral here on the right, but using only the scattered electric and magnetic fields. So that's the total scattering cross section, and we integrate over the whole sphere. So that's why we have an integral over all solid angles. And then we identify within the integron here. This is what we call the differential scattering cross section. So this is a cross section per unit solid angle. Okay. And the phase function is the same, but just relative to the total cross section. And then, well, we defined a couple of useful parameters, which is the asymmetry parameters, and this other one is the Q, which is the ratio of the total cross section relative to the geometrical cross section, which would be that of a sphere of radius A. Okay, if the obstacle is got radius A. So this is all the previous stuff is about linearly polarized radiation. This can be extended to natural light, well, this is big, there's a lot of calculations behind this, and it becomes quite tedious. But suffice to say that you can do it for now, okay, and you can see more or less how it go. So with this, we finally managed to relate the extinction coefficient with the extinction cross section, and the extinction cross sections are themselves related to the vector scattering amplitude here, x, which is itself related to the amplitude scattering matrix. But of course, we've not said how we calculate the amplitude scattering matrix yet. So going back to radius scattering, and this is the case where we have the obstacle much less than the wavelength of the incident radiation, and we saw that in this case we could write the scattered fields this way. Okay, so these are the radiated fields away from the induced dipoles. So this is the induced dipole P. So we include right, so this is the dp omega is the power radiated towards a given solid angle, per unit solid angle. Okay, and we connected with the concept of cross section by normalizing with the incident flux. So the power emitted by unit solid angle in some direction divided by the incident flux. Okay, and of course that depends on polarization. Okay, so here we are selecting E would represent the exit polarization, and E naught represent the incident polarization. Okay, so this is a way to generalize the scattering cross section to include different polarization states. Okay, so it's I know that it's becoming ever more complex. Okay, but this is radius scattering in its full details. And it depends, of course, on the polarization of the incident radiation, and the power emitted in some direction also is polarized, so we can select different polarization states. Okay, so here I'd like to emphasize how we select the incident polarization. Like, look at what's in the denominator here. We are taking the projection of the incident fields onto the complex conjugate of this incident polarization. So why do we take the complex conjugate? Because remember that this vectorial unit vector can be complex, because we are including the possibility of circular polarization. So we went through this. This is a handy way to represent polarization, to select polarizations. If it's linear polarization, then the complex conjugate doesn't do anything because E is just real, okay? But if E is got a phase difference between the two components, X and Y, then we have circular polarization. Bear with me a second, I'll just be a minute, okay? Espérame 2 minutitos. Okay, I'm back. Yeah, I just want to remind you that this projection idea, when we project the this thing here is this E asterisk dot E S modulus square would be the net flux. Well, that's proportional to the net flux or the Poynting vector in polarization state E. So E can be linearly polarized if it's real. If E is real, if it's all in real, and it's linear, and if it's complex, it's elliptical or circular. Okay. So it's circular when the two components are what we call modulus. Okay. And then, yeah, I think that this might seem a little bit surprising, but remember that this Poynting vector is proportional to the amplitude square of the electric field. Okay, this is what we showed. So when we use these, the Rayleigh scattering formula, we end up with the scattering cross-section in Rayleigh scattering. So there's a number of very important features to remember here. Rayleigh scattering means small obstacle relative to the wavelength, and we have this fourth power of the frequency, so meaning that the scattering cross-section increases like the fourth power of the frequency, and all the rest are just properties of the medium or physical constants. Okay, so it's very important to see that the scattering cross-section is proportional to the fourth power of frequency, typical of scattering, of Rayleigh scattering. Okay. And you must have heard that this is the standard explanation for the blue sky, right? Because if you look at anywhere in the sky, then the scattering amplitude is greater for blue light compared to red light. Okay. If we consider the case where the target is a small dielectric sphere, okay, without a permittive magnetic, without mu, sorry, mu is 1, but with an electric permittivity, then the calculation in the static zone gives you the induced magnetic electric field. So I think that this is the end of semester, and just want to say that well, we need to close. You need to hand in your homeworks and you hand in the exam and all that. Of all the homeworks in this chapter, I think this one is not so important. I think you must have done this in the electricity and magnetism courses, so this is not really important to do once again. And so, well, there's one particular homework I really want you to do, and this one is optional. I'll try to send you an email remind you of this, but for now, just try to remember that this one is optional. The scattering cross section in the end is given by equation 42 for this case, for the small dielectric sphere. The case for natural light, so when we are averaging over non-polarized incident radiation, this is what we have for the outcome scattering cross section. Okay. And this is what you get also for in the case of linear polarization. If we select the outcome polarization E, we choose linear and parallel, linear parallel perpendicular. So we select linear polarization only parallel to the plane or perpendicular to the plane. So what does this mean exactly? This is what I'm saying here. We have, this is the incident direction. This is the plane of scattering. So we have theta here. We imagine that the sheet is the sheet is the plane of scattering. Okay. Okay. And so in this case, we have, so this was the incident radiation here. Okay. This is the obstacle. Okay. So that would be so that would be E perpendicular, and that one would be parallel. Okay. And so what this is saying, it's interesting to see that when cos theta is 0, meaning when theta is 90 degrees. So when we have this case, okay, so when it's pi half, then the scattering cross section, the parallel scattering cross section is 0. Okay, so that's interesting. It means that if you look at in this direction, if you look perpendicular to the direction of, if you have light hitting an obstacle and being scattered away at right angles, you'll have no polarization in the parallel plane, meaning that the parallel electric field here is 0. Okay, sorry, this is wrong. What I just wrote here is wrong. This is indeed the parallel direction, but this is the one. So that would be, let me write it down with, so that would be E perpendicular, and this one would be E parallel, of course, not that one. Okay, so let me erase it so we have no confusion. And so here, in this case, we have E parallel and E perpendicular. What I'm trying to say is that E parallel is 0. The scattered field at right angles is 0. This means that in scattering, if you're observing scattered radiation, the scattered radiation is 100% polarized in this angle, at right angles. So this is really important to understand. we have the scattering cross-section for Rayleigh scattering decomposed into two outcome polarization. We have the parallel polarization and the perpendicular polarization. So this would be the flux emitted in this polarization state, perpendicular, and the flux scattered into the parallel polarization state, which corresponds to this one. Okay. So for the special case when theta, scattering angle, the reflection angle is 90 degrees, then we see that the parallel component is 0. Okay, so all of the flux that's scattered away at right angles is necessarily fully polarized. When we have intermediate angles, we have this theta term, then the polarization fraction is proportional to this angle. It's not 100% polarized, but it is somewhat polarized. So you can imagine that this is not at all going to lead to natural light, is my point. Whatever theta, you always have some polarization fraction, even if the incident beam is completely non-polarized. So this is super important in astrophysics because we use this property when we observe something that's being lit upon. So we have this star here that's illuminating some surface. Okay, could be the edge of a molecular cloud, could be a protoplanetary disk, or it could even be a planet, as I mentioned last time. There is hopes to detect protoplanets with the future giant telescope using this technique, where we have reflected light. Okay, so we are observing this direction. So we have radiation hitting this surface here, and this is the angle theta. Okay, so when we have non-polarized light from the star, it hits the surface and is reflected, and reflected light is necessarily polarized. So if you design an experiment where you can select only polarized light using polarizers, you'll only see the reflected light and you won't be bothered by the stellar radiation. Okay, so that is really interesting. Well, I said emphatically, I think, my humble opinion, that this is a very important technique. Especially nowadays, it's very important. I use it for my research, but I think that's going to become ever more important. Good. So this is the polarization of scattered light. Now, when we have several obstacles, we use the superposition principle, meaning the linearity of the Maxwell equations, to compute the scattered cross-section. So this is the scattering cross-section, and we sum up all the scattered contribution, and so, okay. This is a standard development. I'm not sure whether all of you have seen it before. It used to be that, I don't even say Chile, this used to be quite important to go through, but I think that it's kind of been lost from the undergrad courses. Is this diffraction networks, where you superpose the scattered electric fields. So one thing to consider here is that in the radiation zone, when we are evaluating the field at this point X, okay, so this is what we're doing here. And let me write it down. We need a sketch here. So this is the obstacle. We place the origin inside the obstacle. This is point X, and this is point X prime. Okay, and so this thing here is X minus X prime. And you can imagine that this is proportional to R, which is the modulus of X. Okay, it's very close to R, which is the modulus of X. The first order, the first correction is given by this term, n dot X prime, where n is the unit vector, n is this. Is X divided by R. Okay, so you can work this out. It is a Taylor expansion of, well, you do the usual, you need to write this down in Cartesian coordinates and do the Taylor expansion. And so when you plug this in, you end up with this term, the oscillating term here, Q. All the xj sum up the target position. So what we're doing here is that this what I call the obstacle is now would be the obstacle, which is going to be, well, no, I didn't want this. So this is going to be a volume V, which contains the obstacles, a collection of obstacles. Okay. And so the origin now, the origin is within this volume V anywhere. And the point is that we are looking at the outcome very far away from this volume V. And so if we have identical targets, then you can see that you can work out that you have a form factor that factors out. And the form factor depends on the position of all the particles. And if the positions are random, then you do an average over their random positions. This is easy. They just sum up incoherently. It says, we say the word incoherent because they just sum up without doing any diffraction or interferences. And this is the net result. We have the outcome cross-section is just n times, n is the number of obstacles, times the case of a single obstacle, if they are placed at random. But if they're ordered, for instance, as inside a crystal network, or inside a diffraction grating. So inside we have cameras, the spectrographs inside the telescope cameras are composed of gratings, which is they're like this actually. We have inside telescope gratings, we have this sort of things. So we have So this is a mirror, and we have light incident on this mirror inside a camera, and each one will each mirror is going to reflect the radiation in the incident light, in their own direction, but they represent secondary sources. So academically, the first way to look at this is like this. You have the usual case of a screen like this, a conductor screen, and we draw holes in it. So that's one, that's two. So that's what normally we look at when we do a diffraction grating. We have holes separated by a distance d with a size a. So this is d, this is a. Okay, and so this in this case would be d, and the size a is almost equal. But the idea, I'm just doing a long story short, I'm just saying that the case of a cubic network is the general case for a crystal lattice, but it's also relevant in astronomy because we use for two reasons. First, because sometimes we have diamonds in space. I mean, maybe that sounds crazy to you guys, but it's like this. We know of examples of circumstellar disks which shine in diamond spectral features or crystalline features in general exist. And so we do need to consider crystal lattices to compute the scattering cross sections, but we also need them to model and to design the detectors, I mean the spectrographs inside the cameras. Okay, so now I'd like to we want to be able to look at this in detail, the problem of diffraction. And it's not so terribly important for us because the idea here is we're no longer in Rayleigh scattering. We are considering the case where the incident wavelength is comparable, or the observation wavelength is comparable to the size of the obstacle. And of course that can happen if you have a sufficiently big obstacle, or if you're observing in the ultraviolet or the visible light for small obstacles. The point here is that we're not always in the Rayleigh regime. And we can compute analytically the scattering cross sections for the case of conductors. So when we have when the obstacle is a conductor, okay, when we have a sphere, a hard sphere, or a screen with a hole, okay. So whatever surface, whatever conducting surface, okay. So in this case, we need to solve for the fields in space, which are represented with this generic psi, which is a solution of the wave equation, which becomes the Helmholtz equation when we use the harmonic component. Okay, so this is the wave equation in vacuum. Okay, subject to boundary conditions. So we have, this is the usual wave equation, except that we have a problem now. We have this. So we have incident radiation, and this is the scattered field. And that's a conductor. So here we know that E is 0 inside the conductor. And so we need, this is the boundary condition. Okay, you see that the problem is a little bit different, because now we have an idealization that we have the interaction of electromagnetic radiation with conductors. Okay. And in this case, well, of course, this is not the issue. This is not just an astrophysically relevant situation. The astrophysical situation is way more complex. We don't have a conducting surface, we have a dielectric, okay? But this is, however, a very important situation for people who do instrumentation. You know, when you want to design a camera, you need to take into account the diffraction. Or last time Andres had asked a question about the coronagraphs, and the coronagraphs are obstacles at the focal plane of the camera, and you need to take into account the diffraction. And so you design them with a special shape. You give them vortex shapes, you know, like a vortex, you know, it's a conductor with a point, and like imagine the head of a screw, like this, in order to minimize the diffraction patterns. Okay, so we won't go too much into the details. This is a standard procedure to solve the Helmholtz equation subject to boundary conditions. We use the green formalisms. This homework I'm not asking you to do. I hope to remember to send you an email. This one you skip. But it's just to show you that you can work out, given the green function, we can work out the fields, okay? And if we have an infinite plane, the one I've drawn here, then the green function is this one, you compute it with the method of images. And then if, well, you have an opening, then you can obtain the fields by using equation 63 here, okay? And this is the result of it. And this is what motivated, well, actually Huygens principle to do, to model the diffraction comes from this idea. But I think Huygens simply arrived at this formula intuitively, saying that, well, inside the opening, we have he imagined a continuum of secondary sources, each one of them emitting spherical waves, okay? We won't be, this is all the scalar case, and the vectorial case is more complex, but I think we don't have time to go into diffraction details, and it's also relevant mostly for people who do instrumentation. So now let's finish with mis-scattering. So I've got good news. We won't be doing any more tedious calculations. Okay, this is the end of the course also, so there's no chance. Just want you to look at the situation we have now. Back to the scattering problem. Okay, so we have an obstacle. No, let's say it's a sphere. Okay, good, it's a sphere. Mis-scattering is for a dielectric sphere. Okay, and we have incident radiation. Okay. Now, the incident radiation interacts with the sphere and induces dipoles. Okay. We could work out the scattering cross section and the scattered fields when what we just did is compute the scattered fields using the Rayleigh scattering. Rayleigh scattering is okay when we have lambda much greater than d. But what happens when lambda is over d? Then in this case, we have a problem here. When lambda is over d, we can't use the Rayleigh scattering formula anymore. And even though we have induced dipoles, then we can't just say that, well, this is all equivalent to just one dipole P. We had the Rayleigh scattering, which said, well, we have induced dipoles, and the net result of all this interaction here was that it induced a dipole P. So we had this dipole P, which was given by the, so this is the polarization inside the induced polarization inside the sphere. And this is what was oscillating and re-radiating the scattered fields. But in this case, if lambda is avoided the obstacle, then we can't use the Rayleigh scattering anymore, and we need to solve for the Helmholtz equation in a similarly as a scattering as a diffraction problem, but we don't have a conductor sphere anymore. Also, so it's even more complex. If it's not a conductor and if it's a dielectric, we use the boundary conditions at the interface of two dielectrics. One is inside the obstacle, two is outside. So you must remember this from when you did the electricity and magnetism courses, when we had two regions and we had a boundary across them. Then we had discontinuity conditions. The parallel component of the electric and magnetic field had to be continuous across the boundary. This rings a bell, right? When we did when you had like an interface between two dielectrics, then you had the parallel component of D and H was continuous, and the perpendicular component of D and B were continuous. Okay, so this is what we apply here to calculate the solution of the Helmholtz equation subject to these boundary conditions. It's horrible. The rest is horrible. The solution comes from an expansion in polynomials, and you have an expansion in series. So the solution is scattered fields that are expanded into these two coefficients, which depends on Bessel functions. And well, the math behind it is quite complex. Is given into the textbook by Boron and Hoffman. Okay. The final cross sections are given by the scattering and extinction cross section. Yeah, so this is scattering, and this is the total cross section. And you can also compute the amplitude scattering matrix element using these coefficients. Okay, but of course you can imagine that this is all numerical work. These are the formulas. You can also compute the phase function resulting from this problem using this standard development. And well, of course, I don't do this. What I do is use packages of people who solve the problem for me. Here is an example package written by Keith Doulemont, where he actually inherited the Baranov Me code, which I think was written by Bruce Drain. It's available in Wikipedia, but I recommend to use the Python interface written by Keith. It's much easier. And in the end, we have these results. So this is the opacity per unit mass. Okay, we have absorption. These are different cases where we have the blue line. Oh, we don't see it. Let's look at the orange line. The orange line is the absorption with smearing. Smearing meaning without smearing in grain sizes. Well, let's look first at the green stuff. Let's look at the green. Okay, no, sorry, I'm being confused now. I'm being confusing. Just look at the absorption one, the first line, the blue one, and it's this. The blue one is underneath the orange curve. This is the absorption cross section, and this is the absorption cross section. and the blue line becomes start to show some oscillations. These are resonances close to the case where lambda is close to the size of the obstacle. So from memory, I think the lambda, the size of the obstacle is 1 micron here. So when lambda is of order 1 micron, which is here, we start saying resonances, okay, which are related to the resonances that are drawn here in this artist impression. When we are away from the size of the when we reach a regime when lambda is much greater than the size of the obstacle, then we see the 1 over when we see that the absorption cross section decreases. But more interestingly is the scattering cross section in green and red. So let's focus on the red line now. Scattering cross section shows big oscillation for one size or a single grain size, but when you average over distribution of grain sizes, these oscillations are damped a little bit. And when you go to the regime where lambda is much greater than the size of the obstacle, you go into Rayleigh scattering, which is this scattering cross section that decreases steeply. This is the same plot, but plotted with in terms of Q, which is the scattering efficiency, this cross-section divided by the size of the obstacle as a function of the grain size parameter. This is another way to plot the same calculation. And this is an example scattering phase function. So look at the orange line. So this is phi, the scattering phase function, as a function of angle. So 0 means forward scattering. We have a big peak, forward peak here. Okay, the grain size is 10 micron. This is the radius of the dielectric sphere, 10 micron. And we are observing at 1 micron in the infrared. A strong forward scattering peak, oscillations which are related to these blobes here. These are the oscillations. Of course, in this case, it's azimutally symmetric. So we have oscillations all the way to 180 degrees. So this is backward scattering. This is reflection back into the direction of the incident beam. And when you do the average over a grain size distribution, you get the blue curve. Real life is not made of hard spheres. Real dot grains are not spheres. And so we expect that in real life, these resonances do not exist, and we are, it's better to do some averaging over maybe 20% distribution in grain sizes to obtain the blue curve, which is more realistic. Okay, so this simple homework is what I would really like you to do, is to reproduce this same plots, but for a 1 millimeter size grain, composed of pure graphite, and compute the grain albedo, and plot the phase function at a wavelength of 1 millimeter. So this is the single homework, I think, from this whole chapter, which is the most important one, because in the end, this is the practical result of all we've talked about. And so just to summarize, if I go back through the whole chapter, let's see which homeworks are important. I think this one is important. The first one, this is not important. Well, I think this is, I mean, this you should do if you want to understand polarization by reflection, really. But this is all, no, we said we didn't do any of these homeworks. So, right, so to summarize, we have only 3 homeworks here. La primera tarea, first homework is this one. It should be fairly easy. It's done in the Bohr and Hoffman book, which I'll upload now. The second one is this one on Rayleigh scattering. This one is optional, not if you want to do it, but this one you should do. I think it's important to understand the reflection of polarization by reflection. So please try to do it. And the last one is the one, the numerical calculation of the Mie coefficients. Okay, guys. So I hope that Pratyush and Nitya could follow despite the internet issue. Otherwise, I'll just upload the recording now. And I know that this is really difficult, but it's advanced stuff. But this is as far as we get. I mean, the rest of it, all the I mean the rest of the chapters about these relativistic phenomena, strict proton scattering, and is that part is actually not so difficult because it's hard in practice, it's hard in theory, but then in practical terms, it's just plug and play, just given an emissivity and you use it to calculate to make your calculations. The radiation part is more complex. The radiative transition part is more complex, and I'm really sorry we didn't have time to go through that. But if you need it for your research afterwards, then please let me know. So with this, we'll mañana hemos entendido, estoy terminando la clase. Quédate en línea nomás. So with this, I think we finished what we could do on the course given the conditions, and I hope it's going to be useful for you. And that's it. So please hand in the homeworks at your earliest convenience, I think is the way to say it. Okay. Bueno. With this, I say ciao. I'm available.
Professor, I have a question before leaving. How much of the tareas we have to do, because okay, so for the last presentation we have to do the three you mentioned. But for the other, we have to do all of them.
I think they're easy, Felipe. See?
Well, I mean, yeah, but
I mean, if you have
just to be clear, yes.
Okay, Felipe, I think you do well in asking. So we normally what I said last time I did the course is said 60% of the homeworks, but we did the whole chapters. Okay, and we had an exam also on top of it. So in this time, we agreed we would not be doing an exam, and we were replacing with the homeworks, but we do all the homeworks. Okay. However, sometimes I might not really calibrate the level of difficulty or the level of work required to do the homeworks. Okay. If it becomes too tedious, I am open to discussion and to reconsider. Okay. This is what I think you should do to try and absorb the material we saw. If you do the homeworks, I can then vouch for you guys having learned this part of the course. Okay. It's okay to do it together. It's okay to discuss them. I just need you to hand in your own version, so make sure that you actually wrote through it. You know. But if that part becomes too tedious or representa demasiado trabajo, you have to say, tell me. Okay. And I'm open to reconsideration.
Okay. Thank you.
Okay. Bueno, me despido. And well, I hope you can find some relaxing times in this long weekend now. Ciao.
Thank you very much, Professor.
Okay, bye, Nitya. I'm glad to see that you're online.
Goodbye.
Ciao.
Bye.